Hello everyone. Today I will present our production framework for estimating heterogeneous treatment effects in online advertising experiments. The core idea is a hierarchical Bayesian model for aggregating effects across thousands of noisy ad campaigns. Why is this problem hard? Performance advertising is judged on conversions, not clicks. The key metrics are cost per acquisition, CPA for short, and conversion rate. But conversions are sparse. They are also diverse, from low-intent page visits to high-value purchases. This inflates the variance of observed CPA, and treatment effects truly vary across campaigns. Targeting, creatives, and auction dynamics are different. The plot shows both issues. The estimates theta hat I have wide intervals from sparse counts and scattered centers from real heterogeneity. So we face two problems at once: sparse data and genuine heterogeneity. The standard baseline is inverse-variance weighting. Each campaign is treated as an independent unit. We estimate a log rate ratio per campaign, then aggregate with inverse-variance weights. In the random effects form, the heterogeneity, denoted here by tau, is estimated with the Paul-Mundell method, but tau is estimated from a single noisy experiment. If we underestimate it, standard errors shrink and false positives inflate. Sparse counts with high heterogeneity is exactly the regime where CPA experiments live. We make three contributions. First, a hierarchical Bayesian model that jointly models campaign-level effects and cross-campaign heterogeneity and stays stable under sparse conversions. Second, Bayesian sequential testing with decisions based on HDI and ROPE, recomputed hourly as data accumulate. Third, deployment at scale. The system is used in a demand-side platform handling over 5 million requests per second, with more than 35,000 campaigns and 3,000 advertisers. Now the model itself. We model conversions with Poisson regression. For campaign I and variant j, the conversion count is Poisson with mean lambda ij. On the log scale, lambda ij equals alpha I plus theta I times the treatment indicator plus log spend as an exposure offset. Alpha I is the baseline log conversion intensity, while theta I is the campaign level effect. The priors induce partial pooling. Alpha I and theta I are drawn from normal population distributions. Low-volume campaigns shrink toward the population mean, while high-volume campaigns keep their own signal. Hyperpriors are weakly informative, scaled in units of the reference effect delta. The key difference from inverse-variance weighting is that theta and tau are inferred jointly, so uncertainty about heterogeneity flows into the posterior of the global effect. For decisions, we use Bayesian sequential testing. We combine the highest density interval, HDI, with a region of practical equivalence, ROPE. The ROPE is the interval from minus delta to plus delta. Effects inside it are practically equivalent to the null. The rule is simple. If the HDI is entirely outside the ROPE, we declare an effect and stop. If it is entirely inside, we declare equivalence and stop. If it overlaps a boundary, we continue. The posterior is refreshed hourly. Delta is calibrated from historical AA tests. A precision stop triggers when the HDI becomes narrow enough. We validated the framework offline with calibrated simulations. The data generating process mirrors production and is calibrated to 5 days of DSP data, 3,000 advertisers with about 9 campaigns each, and CPA and spend drawn log normally. We varied the true effect theta from 0 up to 3 delta and the heterogeneity tau from 1 delta to 10 delta with 200 runs per setting. Importantly, the process is deliberately misspecified. Conversions are negative binomial, while the model assumes Poisson. Here are the main results. Under the null, the type 1 error of inverse variance weighting grows with heterogeneity, reaching 35% at tau equal to 10 delta. The hierarchical model stays close to the nominal level at 6%. Bias tells the same story, 0.02 delta for our model versus 0.3. 2 delta for inverse variance weighting. For power at typical production heterogeneity, the hierarchical model reaches the 80% target. Inverse Variance weighting looks similar on paper, but its high tau power comes from miscalibration, not sensitivity. In short, inverse variance weighting is fine up to about 4 delta, then fails exactly where CPA experiments live. We also validated the framework online with 3 production case studies. The figures shown here are simplified to highlight the key findings. The full results are reported in the paper. First, an AA validation. The posterior converges to 0, and the HDI falls fully inside the rope at 72 hours. This validates the pipeline end-to-end. Second, a new CVR model with a lift of about 2 delta. The HDI clears the rope after roughly 32 hours, so we stopped well before the 5-day horizon. Third, a creative retrieval model. The effect is about 1 delta, and the HDI is above 0, so conventional tests would ship it, but the rope tells us the effect is too small to justify the rollout. These case studies illustrate 2 main advantages of this approach. First, we can stop experiments much earlier, freeing up traffic and time for other tests. Second, we can distinguish statistical significance from practical significance, preventing us from rolling out changes whose effects are real but too small to matter. 3 takeaways. First, choose the method by regime. The hierarchical model matches inverse variance weighting at moderate heterogeneity and is markedly more reliable when heterogeneity is high. Second, HDI with rope turns posteriors into decisions in business units. In particular, statistical significance does not imply practical significance. Finally, the framework runs in production today, informing platform-wide rollout decisions. This brings us to the end of the presentation. Thank you for listening.